welcome to GER Hall Mathematics and Statistics lessons. In today's video, I'm going to be talking about the distributive property of a binary operation. If you've really enjoyed our videos so far on binary operations, on the closure property, commutative property, and associative property, please give us a comment in the comment section. We are going to be talking about the distributive property in this particular video. Please smash a like on the video and endeavor to subscribe to the channel if you haven't subscribed, and I will see you in this video. To my class on distributive properties of a binary operation. Okay, so in this video we are going to start with answering the question, when is a binary operation distributive over another binary operation? Now I must start with explaining this very important point because it is something very important for you to know in order to understand our property called the distributive property of a binary operation. So the question is this, or the statement is this rather. In the commutative property of a binary operation, remember it was one binary operation that was defined on the non-empty set. When we went into discussing the associative property, we also defined one binary operation on the non-empty set. But I want you to know that when it concerns the distributive property of a binary operation, there are two binary operations involved. So we talk about one binary operation being distributive over another binary operation. So distributive property pertains to two different binary operations, okay? And that is what I want you to know before we start with the property. So that being said, let us see how we can state the property. So the question is, what is the distributive property of a binary operation? Okay, so I'm going to start this way. Let asterisk and nabla be two binary operations. Let asterisk and nabla be two binary. This symbol is called nabla and this symbol is called asterisk. So let asterisk and nabla be two binary operations defined on a non-empty set. Defined on a non-empty set X. Then asterisk is said to be distributive over nabla if and only if the following holds. If and only if the following holds. Now, under what condition? Remember, there are two binary operations in this case. When you talk about distributivity, there must be two binary operations in question. In this case, I am using asterisk and nabla to represent two different binary operations that are both defined on the non-empty set X. Take note, this non-empty set must be closed. Remember, we said it in our earlier videos on commutativity and on associativity, that before talking about defining a binary operation on a non-empty set, that non-empty set must be closed. And by the closure property, remember, we talked about two elements selected at random from a set combining to give an element in that same set. Implies that the set is closed. Okay? So if you are talking about the distributive property, it must be two binary operations involved, both of them defined on the non-empty set. Now, you must also take note of one thing. If in this case I have taken asterisk and nabla to be two binary operations defined on the non-empty set, either of them can distribute over one another. So in this case, I'm starting with considering the case where asterisk is said to be distributive over nabla. So we want to see the condition. Under what condition would we say asterisk distributes over nabla? So I am saying asterisk is said to distribute over nabla if and only if the following condition holds. So let's see the condition over here. Now, if it happens that A asterisk B nabla C gives the result A asterisk B in bracket nabla A asterisk C, or I'm going to call this an equation 1, or it so happens that B nabla C asterisk A is equal to B asterisk A in bracket nabla C asterisk A. Now, I'm calling this equation 2. If it happens that A asterisk in bracket B nabla C equals A asterisk B in bracket nabla A asterisk C, or it so happens that B nabla C in bracket asterisk A gives the result B asterisk A in bracket nabla C asterisk A, then and only then can we say that asterisk is distributive over nabla. In this case, this would happen for A, B, and C elements selected from the non-empty set. So let us go over it quickly again. When is a particular binary operation distributive over another one, both of them defined on a non-empty set? If the two binary operations in question are asterisk and nabla, I am saying that asterisk is said to be distributive over nabla if and only if the following holds. Okay, so if and only if condition 1 or equation 1 holds, or if and only if equation 2 holds. Okay, now let me remark here in this case, note that equation 1 implies, when equation 1 occurs, it implies that asterisk is right, or asterisk is left distributive, asterisk is left distributive over nabla. Now take note of this case in equation 1, when asterisk, in both cases asterisk is distributive over nabla. But if you notice one thing from equation 1, you will notice that asterisk is to the left of the bracket containing B and C operated on by nabla. So asterisk, because it is to the left, implies that if this is true, that asterisk is distributive over nabla, and in particular it is left distributive over nabla. But if it so happens that asterisk is to the right of the bracket containing nabla, and this holds, then we say that asterisk is right distributive over nabla, because in this case it is to the right of the bracket containing two elements B and C operated on with nabla. So in the first case, I want you to note that equation 1 implies that asterisk is left distributive over nabla. Now, what about equation 2? Also, note that equation 2 implies that asterisk is right distributive okay, let's go over here, right distributive over nabla. Now you will notice that equation 1 and equation 2 both describe asterisk being distributive over nabla. And again, take note of what I said earlier on. If there are always two properties, there are always two binary operations defined on a non-empty set when it comes to distributivity, and either of them can be distributive over one another. In this case, equation 1 and equation 2 talks about scenarios where asterisk distributes over nabla. What about the other scenario? Nabla can also distribute over asterisk. So what will happen in that case? More so, nabla is said to be left distributive over asterisk if and only if A nabla B asterisk C gives A nabla B in bracket asterisk A nabla C. So I'm calling this and equation 3. So if equation 3 holds, what we conclude is that nabla is left distributive over asterisk. And why is that so? You will notice that nabla is to the left of the bracket containing two elements operated on with asterisk. Also, nabla is said to be right distributive over asterisk if and only if B asterisk C nabla A equals B nabla A asterisk C nabla A. So I'm going to call this equation 4. So take note of all we are saying in this class. We are talking about the distributive property, and I'm telling you that in distributive property there are always two binary operations. Either of them can distribute over one another, and even when one of them distributes over the other, there are two cases. If one of them distributes over the other, that one that distributes over the other one can be left or right distributive over the other one. If the other one distributes over the first one, then the other one can distribute in left distributivity or right distributivity over the other one. So take note. So equation 1 talked about asterisk, a binary operation, being left distributive over nabla. And why is that so? Asterisk was to the left of the bracket containing nabla. And equation 2 described a scenario of asterisk being right distributive over nabla. And in this case, why was that so? It was because asterisk was to the right or to the right of the bracket containing nabla. Now, if you come with me to equation 3, you will notice that we had another scenario which described the case of nabla being distributive over asterisk. But in particular, equation 3 emphasized that nabla was distributive or left distributive over asterisk. If you come to equation 4, nabla is also distributive over asterisk, but in this case, it is in particular right distributive because it is found to the right of the bracket containing asterisk. So, that being said, let us now go to typical examples of what describes distributive property. So, typical examples of what describes the distributive property is something we've been doing over time, probably in our elementary days in school. Now, let's see. Now, why have we always done this? You will notice that whenever we had 5 multiplying 3 plus 4 in a bracket, our answer gave us something like this. 5 times 7, which in turn gave us 35, okay? Now, you will notice that this result was the same as doing this. 5 times 3 plus 5 times 4. In this case, 5 times 3 would give 15 and 5 times 4 would give 20, amounting to the same result as 35. Now, in ignorance or unconsciously, this goes to show you that we have been applying the distributive property all along. What it means in particular in this case is that multiplication, notice that outside the bracket there was a binary operation, and that binary operation was multiplication. Within the bracket there was another binary operation which was addition. Okay, so the reason why 5 times in bracket 3 plus 4 was equal to the same thing as 5 times 3 plus in bracket 5 times 4 was simply because multiplication as a binary operation was distributive over addition. Okay, now you will notice that multiplication is not only distributive over addition, it is both left and right distributive. And for that reason, we can also write this 3 plus 4 in bracket times 5 gives you 3 times 5 plus 4 times 5. This shows you that addition, multiplication is both left and right distributive over addition. Okay? Now, why do you think in our elementary days we never got to establish a result like this? On the other hand, we never had a thing like this to be true. So we were never taught this in school, that 5 plus in bracket 3 plus 4, which ordinarily would give you 5 plus 3 plus 4 is 12. Okay? 3 times 4 is 12, and this would have amounted to giving you 17. Okay? Ordinarily, this is the right computation for this. Now, we never were told this, that 5 plus 3 times 4 in bracket will give us the same result as 5 plus 3 times 5 plus 4. This was not true and still remains not true. So this is not true. And why is that so? This tells you that addition has never been distributive over multiplication, whereas multiplication remains distributive left and right over addition. Okay? So these are typical examples of where all along the line we've applied the property of distributivity. Now let us take concrete examples on how they are used, how the property of distributivity is used in the concept of binary operation. So I'm going to show you this. Okay, so let's take as an example, I'm going to call this example 1 under distributive property. I'm going to call this example 1. So, given that a binary operation, asterisk and another binary operation, nabla, are defined, given that a binary operation asterisk and another binary operation nabla are defined on R, the set of real numbers, by A asterisk B equals A times B over 2, and A nabla B equals A plus B minus 2. Then show whether or not asterisk distributes over nabla, and whether or not nabla distributes over asterisk. So this is a question I'm going to use to show you how to operate on binary operations using the distributive property. So let us quickly get this done. So I'm going to leave the question there for you to focus on, and let's see how to go about it. Now, like I told you earlier on, when trying to solve any examples of binary operation, endeavor to quote or state the property. So I'm going to do this first of all. So as a solution to the problem, let's start this way. So I'm giving A asterisk B to be A B over 2, and I'm told that anything nabla B, that's A nabla B, is A plus B minus 2. And I'm told or required to show whether or not asterisk distributes over nabla and whether or not nabla distributes over asterisk. So what I'm going to do in this particular question is to use the left distributive property of asterisk over nabla and the left distributive property of nabla over asterisk. So I'm not going to do both ways. I'm not going to be using the left and the right. So I'm going to be doing the left in this video, and I want you to try using the right and then comment in the comment section below. Okay, so if you get that done, drop a comment in the comment section and I'll follow up from there. But in this particular question, I'm going to be using the left distributive properties of nabla over asterisk and asterisk over nabla. So I'm going to start with saying, if asterisk distributes over nabla, then A asterisk B nabla C must be equal to A asterisk B nabla A asterisk C. So if indeed asterisk distributes over nabla, then this should be true. So what is our focus here? We want to show, first of all, that asterisk distributes over nabla. And the condition for asterisk to distribute over nabla is simple. If asterisk distributes over nabla, and in this case I'm using the left distributive property, then A asterisk in bracket B nabla C must be equal to A asterisk B in bracket nabla in bracket A asterisk C. So what you have to do to check if asterisk distributes over nabla is to check if the left hand side is equal to the same as the right hand side. Okay? So we are going to get this done by doing this. So this is where I'm going to start from. I'm going to start here. Now, A asterisk B nabla C is what we start from, or where we start from. So I'm going to assume that my result is unknown. So I'm going to start again with saying let B nabla C be equal to K. Then A asterisk B nabla C reduces to A asterisk K. So I'm using K to represent everything in the bracket here, B nabla C, implying that A asterisk whatsoever is in bracket will now reduce to A asterisk K. Now, how did we define A asterisk anything? We define A asterisk anything as the multiplication of A and B all over 2. So it implies that by that definition, A asterisk K will be the product of A and K divided by 2. Okay? Now, let's move ahead. But we know that K was defined to be B or assumed to be B nabla C. So I'm going to introduce in place of K in bracket B nabla C. And this will now be A in bracket B nabla C over 2. So what was the definition of 18 nabla another thing? We were told that 18 nabla another thing is the addition of both of them with 2 subtracted from the result. So in this case, this becomes A in bracket B nabla C, according to this definition, will be B plus C minus 2. So I'm going to put here B plus C minus 2 in bracket all over 2. If you expand to get the simplified result, this will give you A times B giving you AB plus A times C giving you AC minus A times 2 giving us minus 2A all over 2. Now, what have we done? We've been able to get a result for the left-hand side of this condition. Okay? We have established a result for A asterisk in bracket B nabla C. Now, what we now do is to go over to the right-hand side. Remember, asterisk is said to be distributive over nabla only if the result we get for the right-hand side equals the result we get for the left-hand side. Now we have established a result for the left-hand side, and it is AB plus AC minus 2A all over 2. Now, if it happens that the result we get for the right-hand side equals the result we get for the left-hand side, then and only then would we conclude that asterisk distributes over nabla. But if the results are divergent, that is, they are not equal, then we would say that asterisk does not distribute over nabla. So come with me and let's go over here. Now, so what am I going to do? I'm going to continue with the left-hand side or the right-hand side in this case. So A asterisk B in bracket nabla A asterisk C. I'm going to call it an unknown. So I'm going to say let A asterisk B be equal to I, and let A asterisk C be equal to J. Therefore, if I do that, then A asterisk B in bracket nabla A asterisk C reduces to I nabla J. Okay? So what, according to the definition of nabla A nabla B, would we get for I nabla J? It will be I plus J minus 2. Remember, 18 nabla another thing is equal to the addition of both of them with 2 subtracted from the result. So, and that gives me what I have over here. I nabla J is I plus J minus 2. Okay? Now, having done that, we will now introduce what I is. Remember, I is A asterisk B, so I'm going to put A asterisk B in place of I here, plus what J was represented with, which is A asterisk C. So I'm going to put A asterisk C here, minus 2. Now, come over here, A asterisk B will be defined as, if you look over there, you will notice we have AB over 2. So I'm going to put here AB over 2, the product divided by 2, plus A asterisk C will be AC over 2 by that same definition, and all minus 2. Now, if you simplify this, the common LCM, or the LCM rather, is 2. This is over 1, so the LCM is 2. Now, 2 in 2 would give you 1. 1 times AB gives you AB. Plus 2 in 2 will give you 1. 1 times AC gives you AC. Minus 1 in 2 gives you 2. And 2 times 2 will give you 4. Now, notice that the left-hand side result is not the same as the right-hand side result. So we are going to make a conclusion here. Since the left-hand side is not equal to the right-hand side, then we conclude that asterisk does not distribute over nabla. Okay? So, since the left-hand side is not equal to the right-hand side, it means that asterisk does not distribute over nabla. Now, the next thing we shall do in this same question is to go to checking whether nabla distributes over asterisk. Okay? So, let's see how that is done. So, let us check if nabla distributes over asterisk. Okay? So, we are going to say here, if nabla distributes over asterisk, then we would have a nabla in bracket b asterisk c is equal to a nabla b asterisk a nabla c. Okay? In this case, this is the condition that must be met if nabla is to distribute over asterisk. So let's again start with the left hand side, and this is my right hand side. Okay? So a nabla b asterisk c, let's start from there. We'll call it an unknown. Now I'm going to do the same thing I did earlier on. Let k be equal to b asterisk c. Now if k is equal to b asterisk c, then a nabla b asterisk c reduces to a nabla k. Of course, you would agree with me. Okay? So the question is, what is a nabla k? Now we were told earlier on that 18 nabla 18, or another thing, will give you a nabla k, but a nabla k is equal to a plus k minus 2. But the a, however, or the k, however, is b asterisk c. So this becomes a plus k minus 2 reduces to a plus b asterisk c minus 2. And that becomes a plus, what is b asterisk c? Our definition required us to multiply the 2 and divide by 2. So this is what you are going to have. If you take LCM of this 1 and 1, 1, 2, 1, it will give you 2. So now 1 in 2 is 2. 2 times a will give you 2a, plus 2 in 2 is 1. 1 times bc will give you bc, minus 1 in 2 is 2. 2 times 2 will give you 4. So your result for the left hand side is 2a plus bc minus 4 all over 2. Now, again, we are going to check if the left hand side result is equal to the right hand side result. So let us go over to the right hand side result. What is the right hand side result? So now a nabla b asterisk a nabla c is an unknown. So I'm going to use again I and j. Let I equal a nabla b and let j equals a nabla c. Okay? Then what happens? A nabla b asterisk a nabla c will reduce to I asterisk j in this case. Okay? Now, and that brings me to my final result over here. Okay? So let's come over here and get a final result on that. Now you will notice that a nabla b asterisk a nabla c, or a nabla b asterisk a nabla c, which is now equal to I asterisk j, because we have used I to represent this and j to represent this, will give us ij all over 2 by that definition. Now, this simplifies to what is I, a nabla b, times what is j? A nabla c all over 2. What was defined to be A nabla b? A plus b minus 2 in one bracket. What was defined to be A nabla c? A plus c minus 2 all over 2. Now, if you notice one thing, we can expand from here, even though it is very clear that the result may not be the same. So let us quickly expand. I'm going to use a to multiply everything in this bracket, and that will give me a squared plus ac minus 2a. I'm going to use b to multiply everything in this bracket, and that will give me plus ab plus bc minus plus 4. Okay? Then finally, using 2 to multiply everything here gives me minus 2a minus 2c plus 4. Okay? Now clearly, no matter how you simplify this result, 4 plus 4 ordinarily gives you 8. This tells you that we can conclude that since left hand side is not equal to right hand side, then nabla does not distribute over asterisk. Now, I want you to go over this video all over again, go over the video from the beginning to the end, endeavor to watch in detail and meticulously to get the key points out of what I have explained so far. Remember, we have discussed the distributive property and I've shown you typical examples of what we've done over time on the distributive property, and with this example looked at in detail, you will come to realize certain things you ought to know about the distributive property. Please smash a like on this video and endeavor to subscribe to the channel if you haven't subscribed, and I'll see you in my next class on binary operation. Thank you very much.